Good evening. That's your part. Excellent. I love saying good evening when the sun is still out. With this coming of spring, it makes staying on campus later all the more enjoyable. It's just a beautiful evening. But good evening again. I'm Jonathan Millen. I'm the Dean of the College of Arts and Sciences here at UNE. And this is an extremely exciting time for all of us because we are in the midst of a very impressive array of events on campus. And before we start with tonight, I just want to sort of remind you of where we've been and where we're going in the next couple of weeks. Right before the break, we had the President's Forum, and by all accounts, that was one of the most remarkable events to live up to the vision of that program since its inception. And also right before break, we had a Core Connections lecture, the first Core Connections lecture that we had since the onset of the pandemic. Then this week, we have the Bush Lecture, which is this Thursday night at 5 o'clock in the Forum, and I hope to see you all there. And of course, we have tonight's Ludcke Lecture, which I'll come back to in a moment. This coming Monday on the Portland campus, we have the next lecture in the Center for Global Humanities. And on Wednesday, where is Mike? We have a sabbatical talk from Mike Archero, who's here with us this evening. Now, when you consider this collectively, this is an unparalleled array of speakers and programs. And even more, they represent the heart and soul of what a liberal education is. Exploring ideas and perspectives from across the disciplines in the spirit of lifelong learning, engaging in discussions in which we may disagree with viewpoints of others, but the goal is still to increase a deeper level of understanding all around, and discovering topics for the first time that arouse our curiosity and they compel further investigation. While it's true that much of a college education takes place in the classroom, a vital component actually takes place between those courses, but in lectures, in symposia, in programs, and in an event like tonight. And tonight's Ludcke Lecture is a perfect example. And as a reminder, the Ludcke Chair honors senior faculty members who are among UNE's most distinguished scholar teachers. Indeed, to be a Ludcke Chair is to be nationally and internationally recognized in one's field. This award celebrates the importance of vibrant, original, ongoing scholarly activity that is central to the mission of UNE and to the College of Arts and Sciences, and the educational importance of modeling and sharing that scholarly activity with our students. Tonight represents the third Ludcke Lecture of the year, which is in and of itself remarkable. And while earlier topics came from the environmental sciences and the humanities, tonight we will hear from one of our resident mathematicians, and more specifically, Dr. Craig Tennenhouse will talk to us about wicked hard math, which for some of us is synonymous with math. Dr. Tennenhouse is an expert in graph theory and game theory who has an impressive track record of engaging students in his scholarship. He also has made an ongoing commitment to incorporate that research into the courses that he teaches here at UNE. So as such, he seamlessly weaves together for his students the inherent value of both the classroom education and extracurricular learning, which lies at the heart of both the Ludcke Award and, more broadly, a liberal education. So please join me in welcoming and congratulating Dr. Tennenhouse.
All right. Thanks so much, Dean Millen, for the kind words, for the invitation. Thank you to all of you here in person and everyone logged in via the stream, I guess. Everyone's socially obligated to be here and otherwise. I appreciate you showing up. I titled this talk because I have imposter syndrome like most academics, and I figured it would scare most people away. So we'll see how that does. Also, art I'll talk about here in a little bit. This was done by my daughter, who is watching right now from her dorm room. So how hard can math be? I'm going to talk today about how hard math can be. Also, a friend recommended I do a chalk talk, but this is the best I can do. As a mathematician, we like chalk. I did have a font that was chalky, but it got lost in the PowerPoint shuffle. So I'm going to talk about how I got here in mathematics and how I made it to UNE, what I've been doing since I've been here, the type of work I've been doing, and what I'm planning to do in the relatively near future. The far future, I've got no idea, but we'll see. So first things first, mathematics is fundamental. What I mean by that is that it doesn't depend on anything. It's not created. You can argue, I guess. That's for the philosophers to have that argument. But it's not generated by anything. It just is. So I'm going to use some examples of work from some of my colleagues who work in some really important areas. As we heard from Dean Millen, we've had 2 other talks this year from some of my peers here on campus, and we've had a number of other experts in a lot of areas, and I'll mention those a little bit. So let's go look at history and literature here. First things first. Super important work. This is a Gutenberg Bible. It's a public domain, so it's easy. Really important work. There's a lot of research in literature. There's a lot of historical research that's really, really important, really valuable, and I love what we're able to get from it. But if we go back in time a little bit, we hit a point before literature. We hit a point before history. Let's go back a little bit further. We've got a colleague that studies birds, right? Noah presented a little while ago. I'm partial to the goldfinch myself, so I included the photo up here. Really cool work. We saw an awesome talk from an ornithologist earlier in the year. And I love seeing the science that's coming out of this and a lot of the humanities work that's coming out of our environmental studies program here. But go back far enough, and we don't have birds either, right? Go back a little further. I don't know what this is. I'm not a biochemist, right? We go back far enough, there isn't much other than chemistry, right? Within a fraction of a second of the Big Bang. But we could go back a little further than that, couldn't we? We could. And we just start with these, right? What are these? These are prime numbers, right? These are the primes. They're fundamental, right? A prime number is an integer that isn't that only has factors of itself in 1. Can't break it down into a rectangle of other of dimensions at all. And they've always been 2, 3, 5, 7, 11, 13, on and on. They always will be. It's fundamental. And so mathematics is kind of like this basis on which all of reality is anchored in a way. It may not be as important as some of these other things, but that's okay. All of us as scholars, we don't do things because they're important. We do things because we're drawn to them. So that's what I mean when I say mathematics is fundamental. And I'll talk a little bit about that more as we go. But to give you a little background on me, my education, high school was hard. I had a hard time at all levels. High school was hard. I went to the Indiana version of the Math and Science Academy. We've got MSSM here. I was one of the first graduating classes in the Indiana Academy for Science, Math, and Humanities. It was a school full of people that just made me feel pretty dumb. But high school was really, really tough. And then I went away to college. That was really hard too. Hard time. And then I joined the Frisbee team in college. We still have a Frisbee team here at UNE. I'm the advisor. Talk to me if you want to join, right? I try and run around with the kids the best I can. But I was on the Frisbee team in college, and we took a van from Chicago out to the Rocky Mountains once for a big tournament. And I got out in the middle of the night to call a nature in the middle of the night. And I looked up, and I'd never seen so many stars. And I said, you know what? I'm going where there's stars. And so I only applied to graduate schools in Colorado, about 6 of them. Got into one, and I went. And it was a really, really good time. I had a great time. Unfortunately, my office had a window, so I didn't finish. If you got a view of the Flatirons out in Boulder, Colorado, it's hard to get a lot of work done. We've got pretty nice views here, though. This is pretty incredible. Anyway, dropped out of grad school, decided I don't really like math that much. It's hard. It's I didn't use the word wicked yet. But it's hard. And I met my partner, had a couple of kids, and then decided to go back to grad school on hard mode. So at that point, I went back full time. I had a toddler and a preschooler. One of my favorite memories is standing at a huge window in my old house converted to apartments, using it like a whiteboard with my 5-year-old at my feet trying to draw the same pictures I was doing. I love it. It's awesome. My other kids sitting on my lap, they're both listening right now. They've promised me that they're watching the stream. Incredible memories, incredibly hard to finish up. 2 things I realized in grad school was that I love teaching, absolutely love it. You know how the feeling is, right? When you get in the classroom, you've got a stuffy nose, maybe you got a headache, something like that. You go into work and you get out of the class and you just feel fantastic. It's the best thing in the world. It's absolutely amazing. Research was an absolute slog. I worked with awesome people, my supervisor, my research committee, but it was hard. I didn't want to do research. I thought I'll apply to some jobs that have to do a little research. Maybe I can eke out tenure when I get there. I have enough irons in the fire, but I really, really just want to teach. And so I ended up here, out in Maine, at UNE, which is as beautiful as the Rockies. It's amazing here. We're incredibly fortunate to be here. So I thought I'd use some of the time today to talk about what mathematics research actually is. I didn't really even know what it was when I was an undergraduate. I barely learned my first couple years of graduate school what mathematics research actually is. I had friends who just assumed I added really big numbers together, which is perfectly reasonable. Like, why would you think otherwise? So we'll talk about that. Firstly, what does it mean to do mathematics research? One of the things that mathematicians do is we take problems that everyone else knows the answer to and verify that they're actually correct. So the best example for this, it's called the sphere packing problem. Has anyone here heard of the sphere packing problem? I know of at least a few people who have. So the sphere packing problem is thousands, literally thousands of years old. How many oranges can you fit in a crate? Yeah? Or how many equally sized spheres can you stack up on a table? Right? What's the most efficient way to do it? And for literally over 3,000 years, everyone has known what the answer is, right? You pack them up in this kind of lattice shape or this hexagonal pattern. Anyone who's ever put glasses away from the dishwasher in a cabinet knows the best way to pack circles, right? But there was no proof of it, no mathematical proof of it for literally thousands of years, which is incredible. I ran across this one the other day. Square packing is another problem. And you can actually get really, really efficient if you don't care that much about them staying squares. But in fact, sphere packing gets into higher and higher dimensions. Why do we need that? Do we have higher dimensional oranges? Well, no, but it's a problem and it's there, so it's worth looking into. Thomas Hale in 1998 came out with a particular structure that he built abstractly around spheres, and he proved in a series of papers from 1998 onward that honeybees were doing it right, that this hexagonal pattern was optimal and the most efficient way to pack circles, pack spheres, etc., in 2 and in 3 dimensions. But it took until the late 90s and the early aughts to prove this, which is incredible. The rest of the world looked at Thomas Hale's work and said, great, we already knew that. But as far as mathematics was concerned, this was huge. This was an enormous result because it had been an itch in the brain of every mathematician since there have been mathematicians. So that's what we look at, and they're not always problems that everybody knows the answer to, but they are fundamental problems, right? A sphere is a sphere. So Jonathan introduced me as a graph theorist. That was my first area of research, my first my dissertation was in graph theory for my Ph.D. So let me give you a quick introduction to that. It's what I worked on here for my first 5 or 6 years at UNE. So just to give you a little background, graph theory is, at least the type of graph theory I worked in, was concerned with extremal structures. Structures in pairwise relationships. So things like this. This is an image from one of my papers early on here at UNE. And this is a diagram showing that under certain conditions, we can build structures that are missing particular relationships. And if we add any new edge to it, we get one of those new structures arising. In this case, I'm looking at induced subgraphs. It's not all that important here. We'll get to games soon. They're more fun to look at. But this was a really cool image. I liked it, so I included it here. Another one, I included these. This was a really cool project I did when I really started getting into using the computer for my work. For the longest time, I pushed back against depending on a computer for my work, not feeling it was like pure enough. And then I realized that I could have computers do thousands of things 10,000 times as fast as I could by hand, and it turned out pretty good. This is an example of what are called resolving sets in graphs. Again, from another paper of mine early on in my time here at UNE. And these colored nodes are enough nodes to tell you where every other node is in that graph. I included them here mostly, like I said, because it's colorful and fun, but also because these 3 graphs are examples of things called snarks, which are named after Lewis Carroll's work, which I really like. I try and do as much with a snark as I can because it's great to write it in a paper. It's a lot of fun. There are also graph structures called lobsters, and I have not yet found a way to incorporate them, but I need to do that at some point. And then again, throw the word wicked in there somehow. Lastly, it's kind of hard to make out. But this was probably my favorite graph theory result of mine. This is 100 nodes, and actually all the edges between those nodes are red or blue. We just get this kind of green and yellow because the resolution isn't awesome. That's just the way it is. It's zoomed out. But just to give a quick explanation for what this is an example of a graph that has the following properties. So let's look at this one right here. In this graph, we don't have any red triangles. There's no 3 nodes that are all connected by red edges. And we don't have any blue triangles. There's no 3 nodes that are all connected by blue edges, right? But if we recolor any edge, so let's say we take that blue edge and color it red, we get a red triangle. Or if we take this red edge down here and color it blue, we get a blue triangle. This graph right here is an example of that on 100 nodes. So my result there was that such a graph always exists. It's certainly not going to help cure the common cold. It's not going to make anyone's commute any easier, but it's a lot of fun. And that's the sort of stuff that I look at, these abstract things. So that's what I did in graph theory. The cool thing about graph theory is you can take a network like this and put some Latin words on it and publish a paper with an ecologist, which is awesome. I did this with one of our colleagues here at UNE. These are just food webs. She's not here, and I didn't ask if I could tell the story, but I'll say it. I was meeting with her, kind of bugging her over and over again. Hey, let's talk about graphs. Let's talk about graphs. She's like, I'm an ecologist. I'm like, let's talk about graphs. She's like, I'm an ecologist. Eventually, I started drawing graphs. She said, those are food webs. I said, I know. They're food webs. Let's do a paper. So we wrote a paper together. Pretty cool research. I feel like a lot of what I do as a mathematician is as an apologist for mathematics. And I love the term because it means 2 things. One, I'm really sorry about the trauma you experienced in mathematics when you were younger. So that's the first type of apology. The second is to defend mathematics. It's useful. It's neat. Even if it's not useful, it's still really neat. And as someone who's highly, highly social, I like to work with other people. And so opportunities to do things like this with folks outside of mathematics is a blast. Okay, moving on to games. So I looked at some mathematics of games as a graduate student. I didn't really know much of what I was doing, but I played around with them a little bit. It was good fun. I didn't end up including them in any of my dissertation at all. But when I came out to Maine, I'd been here a few years, and I thought, I wonder if there's anyone studying games here in Maine. So I literally Googled game theory in Maine, and I found someone who happened to be blogging a lot about games. And Kyle and I started working together. It was a decade ago. We looked back at our old messages recently and found out that we were working together. So we visited each other a bunch of times, started working on some projects. I managed to grab an undergrad student, and the three of us worked on a project, presented a paper together. That was a whole lot of fun. And then as we were working through that, Kyle mentioned Lisbon to me. He said, "Hey, Craig, are you going to Lisbon?" I said, "Lisbon?" For an academic conference? It looks lovely. I haven't been to Lisbon Falls yet, but it sounds really, really nice. But I'd lived in Maine a few years. I was like, Lisbon? He was like, no, Lisbon. So we now have a biennial conference in Lisbon, Portugal, though this last year in January, it was here on São Miguel Island in the Azores. It is a hard life. But this was the one in the Azores instead of in Lisbon, still in Portugal. This group of folks, who I just went in January to present some work that I'd done recently, there were 30 talks at this conference, at least 8 countries represented, an incredible group of people. There are a number of undergraduates, I believe at least one high schooler, a lot of graduate students, many postdocs, and then faculty all the way up through emeritus. So loads of folks in awesome positions doing really good work. There's a philosopher present. In past years, we've had historians give presentations. Awesome group of people to work with, and I'm super fortunate to be able to work with these folks. I could probably name 90% of them from the photo right now. And it's a great kind of found family of researchers to work with. So I tell people that mathematicians, we don't need much. We need coffee, we need chalk, and we need other mathematicians. We're a relatively cheap date, right? Chalk is in the closet at the end of my hallway. I buy my own coffee. I guess I could go for a grant for something like that. But then traveling to visit other mathematicians is really, really valuable. And then once you get together, you get to do some things, and you get to like kind of yell at each other at a chalkboard. And that's incredible. And drink a lot of coffee. So that's a hoot. So from there, from that first Lisbon conference, that was like a month before the conference that Kyle texted me, Lisbon? I had to find my passport. It was packed away and like lost. I thought I wouldn't be able to go. Dug it up just in time and went out and started studying games. So analysis of games, turned out I was doing theoretical computer science this whole time and I had no idea. My friend and research buddy Kyle is officially a computer scientist, and we always joke that I do all the coding for us whenever we do projects together. But it's really cool to have like one foot in each of these two areas, mathematics and computer science. The type of games I study they're called combinatorial games. So this is combinatorial game theory that I'm studying. The thing about combinatorial games is that they're very specific types of strategy games or board games. All that you really need to know is that there's no hidden information. So no one's got cards, right? There's no chance, no dice or anything like that. And you take turns. So you're not making decisions at the same time. It's different from what's often just called game theory or EGT, economics game theory. Big difference is that their conferences are funded better, the folks in economics. But they'll slum it with us from time to time, and it's a whole lot of fun doing some combined work. One of my colleagues who I'm actually going to visit on Vancouver Island here in a couple months, right after the semester, does some work in the confluence between the two, economic game theory and combinatorial game theory. It's great. One of the reasons I did this was that it gave me an opportunity to change my research, not just for me to something fun because I like playing games. I mean, we go to these conferences and we do math games all day and then we play board games at night. Like I said, it's a hard life. But it's really accessible to students. Hey, look, it's a game. Everybody knows how games work. There's always this like kind of underlying competitiveness. People know what they're going for. They know what they're trying to do. All we got to do is analyze it a little bit. And I get to ruin fun in a brand new way, right? Here's a game. Why don't I put math in it for you? I love it. I teach a class now on the mathematics of games and puzzles here. Some people know this. And I used it as an opportunity. I use games as a way to teach advanced abstract mathematical topics to unsuspecting students. So I liken it to getting vegetables in a smoothie. They don't know there's carrots in there. They do when they do the homework. All right. So what have I done in games since I started a conference? We're having the 5th one here. Some of the image got lost. That's fine. We're having the 5th one here in a couple weeks. It's virtual. And we've had some in-person ones. It's great. I've had opportunities to have my undergraduate research students speak, my colleagues' undergraduate research students speak, and students from all over. Last year and this year, we've had some students from other countries present, it being virtual and all, which is great. Getting students, undergraduate students involved, and it really doesn't take a lot of background to get them to that point. I co-authored a book with same guy. It's a free PDF. You can pretend to download it in front of me and then erase it immediately after. It's intended, we call it Playing with Discrete Math, it's intended as an introduction to combinatorial games for early undergraduates with very little mathematics background. That was the idea, is that the books that are out there, and I'm friends with some of the folks that wrote them, they're awesome, awesome texts. It's a small group. But we wanted a book that would fit anyone. So I actually use it to teach a different course on discrete mathematics because we built in enough introduction to discrete mathematics, and I just teach intro to proofs through the lens of playing games. So what does it mean to say a game is hard? I guess I should have capitalized the word hard. Hardness is a thing in mathematics. When we say a game or a math problem or anything is hard, we're saying that it meets certain characteristics of being difficult to solve in a way. Solving a game just means finding a strategy for it. Notice I've got a graph here. I'm starting with the number of squares on the x-axis and how much time it takes to figure out the optimal move on the board on the y-axis. So let's start with a chess game. Just a 3x3 chess game. It probably wouldn't take you that long to figure out who would win in this game, whether the first player would win or the second, and what the optimal first move is. I'll give you a hint. Don't move the king first. Right? That's about how good I am at chess. People would assume that I'm good at it. That is untrue. But it doesn't take that long to compute the time it takes to solve this game or to make the next move. And notice I put a little dot down there at the bottom to represent that it's pretty easy to compute the next move. Let's go up and make the board a little bigger. So now I've got 8x8, 64 squares. It's a little harder, right? And by a little harder, I didn't really put numbers on those ticks for a reason. We don't know the optimal first move in chess, right? We know that computers are very good at chess, but computers are still using statistical methods to beat humans at chess. And they're better at that than humans are, but they still don't know the optimal next move. Checkers is solved. We know exactly, and by we, I mean not me, but mathematics knows what the best first move in checkers is for sure. First player can win checkers, first one to move. I just don't know what the best first move is. Chess, however, is incredibly large as far as a game goes. It spans like crazy. It's very wide, it's very deep. Any move you make, right, there are so many different paths to solving this game. There are more possible games of chess than there are atoms in the known universe. We're not going to build a computer that can completely analyze chess. So it's a little harder than this one. Let's make it a little bigger. 16 by 16. I threw some extra queens on there because I thought that would be fun. Who wouldn't want to play chess with a bunch of extra queens? If they were all pawns, that would be pretty boring, right? But I would play this. I guess I could have gotten a picture of Spock playing as 3D chess, too. That would have been good, too. Notice, it's a lot harder. In fact, it's exponential. And so we say this game is EXP time. That means that at least our best algorithms for solving chess take an exponential amount of time to find the next best move when the variable is the number of squares on the board. So as the board gets bigger and bigger and bigger, it gets exponentially harder to solve. Doesn't mean that there isn't a nice solution to the game. It means that there probably isn't a nice solution to the game because a lot of people who are way smarter than me have tried making it easier and they can't. So it's called EXP time. So it's a class of hardness, we say. All right, here are some hard problems, just to give you a sense of it. Chess is probably hard. Parenting is hard. No, the knapsack problem, which I'm going to intro here. This is my family. A few years ago, we hiked across Scotland, up in the Highlands for a week. Those kids are incredible champs. They were, I think, 12 and 14 at the time, and they did it. And those are genuine smiles. They didn't genuinely smile all week, not the whole time, but they genuinely smiled enough. It was great. So I included this picture because we're wearing backpacks, and it's my picture. So the knapsack problem. Let's say I've got a box here. Let's say I've got a box, and it can hold a certain amount of weight. And then I've got a bunch of objects that are all different weights here. And I want to figure out, can I pack this box completely full with these objects, or will there always be gaps? Right? They could be different sizes or different weights, however we want to do it. And that can be a difficult problem, right? Trying to figure out what goes in this other box. Anyone who's ever moved house knows that you've got to try and optimize your space. But if we make the box bigger, it's an even harder problem, right? We make the box even bigger, it's an even harder problem. So just like the chessboard getting bigger, as this backpack or this box gets larger and larger, the knapsack problem gets tougher and tougher. Now, this is an example of what's called an NP hard problem. It stands for non-deterministic polynomial Turing machine. We're not there today, and that's okay. Give me another hour and a chalkboard, and I got you. But this is a different class of complexity. It's not as hard as chess is. Okay. Now, that doesn't mean, though, that we know that it's that hard. And this is one of the things that's pretty tough. There might be a clever way to solve the knapsack problem like that. It may not be really hard to solve. It may be pretty easy, but no one's found an easy way to do it. The thing is, if anyone finds an easy way to do it, then they can also solve the scheduling problem really easy. This is scheduling. Scheduling is also non-deterministic polynomial. It's also just as hard. And protein folding. I told you before I'm not a biochemist. But I am a dad. Okay. Protein folding, there you go. Protein folding is the problem of being given a particular protein and seeing how it folds in on itself. Can you predict what it's going to look like when it's done? And what are its properties going to be? The answer is, well, not really without simulating it in a computer and running tons of computational cycles. Some of you may be familiar with a project called Folding at Home, where people used to, I don't know if they still do it or not, donate their computer cycles. So instead of running a screensaver on your computer when you're not using it, it works on folding proteins. Because there are real applications to that, right? Unlike solving chess. However, if we can solve the knapsack problem easily, or chess easily, then we can solve protein folding easily. There are ways to convert every one of these problems to each other. There's a conversion that turns any scheduling problem into a protein folding problem, and any protein folding problem into a knapsack problem, and any knapsack problem into a scheduling problem. So as long as we have those reductions, they're called, then if one of them is easy, they all become easy. So there's a lot of effort going into trying to find easy solutions for these likely hard problems. Most mathematicians think that there aren't easy solutions to them. I'm in that camp too. Most of us don't think that there are going to be easier solutions than we've found. However, it's still worth finding more of these reductions and investigating them, because if it's ever found, we can not only solve these, but any number of other problems. Cryptography becomes cake, right? You're going to need something stronger than your bank password or however phone encryption works, right? But more importantly, all these other things that actually matter to humans, like protein folding, are going to become really, really easy to solve if we're able to do those reductions. So basically what we do when we look at hard problems is we turn problem A into an easy problem B. And then that means A is easy, right? If we can turn scheduling into knapsack, and knapsack is easy, well then scheduling is easy. Similarly, if A is hard, and we know it's pretty hard, and we can turn it into B, well then we know B must just be as hard as A. So that's what we do when we look at complexity. We look at trying to convert one game into another, or one math problem into another math problem. So this brings us to a board game that's fun to look at. So Nevertafel, I practiced this with my Swedish friend. Nevertafel means the king's table. It's an Icelandic game, and it's based off of all these tafel games. There are a bunch of them. I've got a couple boards in my office. You're welcome to come and beat me at them if you'd like. I love that I can expense game boards. Okay, so tafel is an ancient Viking chess game, which sounds awesome, and it is awesome. I discovered it years ago, actually, when I was in Scotland on that same trip with my family. This is at the National Museum in Edinburgh, Scottish National Museum, and this is a Viking Funeral. They found game pieces in it from, I think, the 12th century, 11th century in Scotland, because there were a lot of Vikings there at the time, and they actually didn't assemble the pieces right in the display, but I'm also going to trust the museum and the archaeologists to do things right. If this is a tafel game, they set it up wrong. But I went upstairs, and they actually have a cool library attached to the museum, and I did a little research when I was there. So I'm going to explain the game and talk about a result I had. This is artwork by one of my kids. I told you that she stood at my feet when she was 4 and worked on the mathematics I was doing, and math had such an impact on her. She's an art major in college right now, and her sister is a senior in high school, also planning to be an art major, which the world definitely needs more artists, and I needed one too. So this is her first commission. I paid her to do this. Hi, sweetie. All right. So this is how tafel works. All the tafel games work the same. You have a king, only one of them, somewhere on the board. You've got attacking soldiers all over the board. There's more than 3, but I'm just giving you a quick setup. And you've got some defending soldiers who are on the same side as the king. Can't tell you how long it took me to figure out how to do that in PowerPoint. Okay. Every piece moves like a rook. If you know chess, rooks move orthogonally as far as you can go. North-south or east-west, no diagonals, no back in time. So you can move a piece like that, right? I'll do it again. This piece can go up to there. And then capture happens custodially. Custodial capture means you don't actually run into a piece, you go on either side of a piece. And if you go on either side of a piece, you take them off the board. And the goal is to try and capture the king if you're the invaders, or for the king to escape to one of the havens, to one of the corner squares. Okay? Cool game. I love it. It's got connections to the north, which I think is really, really cool. And it's got versions all over. Wales has a version called Branduv. Ireland has a version called Ardre. This is the Icelandic version, Nevertafel. There's a Scottish version. I can't remember what it's called. And I'm looking at Branduv right now just because it's a little smaller. But that's what tafel is. So the question is, can we find a way to win tafel easier or easily? And it turns out, no, at least unless we can solve these other games easily, because my colleague and I proved that it's at least as hard as some other games. It's in a complexity class called P-space. It's at least P-space hard, which is a little bigger than non-deterministic polynomial and a little smaller than exp time, and I've already lost you. And that's fine, okay? But it's hard. So we made a version of this game that we could analyze, and the way we did it was we actually built, out of these Toddle pieces, we built logic gates, computational logic gates. And it turns out that if you build the right logic gates out of a game, you can show that it's hard. And it is capable of general purpose computing, basically. So let me show you one. This is an AND gate. The idea, I'm used to gesticulating more. The idea here is that that piece there at G3 can only escape northward if a defending soldier comes up on file D and another defending soldier comes in on file 5. As long as both of those happen, that piece can escape. If one of those doesn't happen, that piece can't escape. And that's an example of an AND gate. So I'm just going to show you how it works, mostly because it's fun to animate. So we bring one up on D, and it takes care of that one. And then, because we're forcing capture, this invading piece has to move over. That's the only legal move it can make there, and takes that piece out of the picture. Now this one coming in on file 5 takes away this one. And then this one on G4 comes over and takes away that one that just came in. And finally, this one on file G can escape. So we just built an AND gate using Toddle. We're not actually going to run a computer using the board game, but we can show, because we can do this general purpose computing, that this is a reduction from another game that we put in a hard, capital H, outcome class or complexity class. So Toddle is probably hard. So that's one of the results I had. There's another one on evolutionary algorithms. I'll just give you a quick intro to it. We don't have as much time as I hoped. But I'm looking at evolution of solutions to problems. So what we do in evolutionary algorithms is we leverage the power of evolution in order to solve math problems, which is really, really cool. We need crossover. We need mutation, and we need fitness. And that's as much as I understand about evolution. The fitness is how strong a particular chromosome is, or a particular individual in a population is in passing on its genes. So in evolutionary algorithms, we do the same with problems. It doesn't look like this sort of thing has evolved, but this is an example of a radio antenna that NASA developed, and it uses evolutionary algorithms. Basically, no person would create that unless you were like giving an exam and the previous professor left a paper clip at your desk, because that's what I always do with them. But say we just load up the computer with a bunch of randomly shaped radio antennas. Maybe some are spinny and coiled up, some are bent up funny, some are straight. And we kind of describe them mathematically. Well, it's this straight, and it's this bendy, and it's this spinny. And then we take the ones that work the best as a radio antenna and shove them together. Sounds really romantic, doesn't it? We engage crossover with their chromosomes. And then we mutate them. And then we take the best ones and we do it again and again. And eventually a radio antenna evolves that no one could have come up with on their own. So we can do the same thing with fitting data points. So let's say we've got a bunch of these functions here. Let's take the blue one and the red one, just randomly generated functions, and I want to see how well they can fit those points. That blue one's pretty good, the red one's okay. We want to do better. Well, we can cross them over with each other. Purple's blue and red. I'm good at color math. That's the best we can do here. We shove those two together randomly, and that's pretty good. And then we can actually mutate it a little bit and get even better. So we can evolve functions to fit points. We can do the same thing for impartial games. I'm not going to give you a quick intro to games. I was going to. But you can consider any game to have a tree of moves. And we can ascribe numbers to every possible move in this game tree. And then the final game itself gets a numerical value. So we would say that the game value of this particular board is 2. or star 2. So what my colleague and I did, Melissa and I, is we showed that we can do the same thing with those dots, finding functions that match things. And we showed that we can do that with game values too. So we're able to find a numerical value for a game using evolution. Super exciting stuff. A couple things I'm doing in the future. So I'm looking at heap games. I'm going to look at these. These are games where you like take some stuff out of a pile and then play the game over and over again, and whoever takes the last piece wins. Like car trip games, right? You start at 21 and you subtract numbers from it, subtraction games. We're looking at heap games and trying to figure out how hard they are. And also looking at temperature. Games have a temperature. A game is hot if making the first move makes a big difference. A game is cold if it's not that important who makes the first move. So we're looking at evolution for the game temperature, figuring out how important the next move is. So that's my next thing, and I actually need a faster computer for it. So I got an order in for a computer. It's the first time I've actually cared about equipment. Hopefully I can figure out how to use it right. But it's nice to have a lot of machines doing a lot of things for me, so I don't have to do them all by hand. As nice as it sounds to tick, tick, tick chalk on the board. So math, fundamental. It's formal. It's not statistics. Can't tell you how often I get asked to do people's regression analysis. I think that's great. I kind of know what regression analysis means. And I know that there's a p-value as a thing. But that is not my knapsack. And it's a game. It's really a game. Mathematics is, we follow rules. We start with some pieces. We move them around right, and at the end someone yells Candyland, and you've proved something. So that's what math is, and that's what I've been doing, and that's what I like spending my time doing. So thank you all so much for listening.
Got a Q&A mic here if anyone has a question.
So I'll admit it, I didn't get it. When you go back to the knapsack problem,
Yeah?
I was picturing packing a car because you had a box, and you said if you had a bigger box, it's harder. And I thought, wait, I'm not following something.
So it's harder to know at first glance whether or not you can pack it to the brim. So if I have a really small box and a bunch of items, then it only takes me a while to figure out whether or not I can pack it to the top without leaving space. But if I have a huge box, I've got to try a bunch of different things, take pieces out, put pieces back in, etc., to figure out whether or not I can
So
do
the
it.
number of pieces keep expanding with the size
The
of
number
the
of
box.
pieces and the number of errors you're going to make in like overloading it or underloading it, things like that. You might load it up all the way and have like, you know, a tiny gap left, and then you got to unload a bunch of things later, right? Thank you.
Hi, Greg.
Hi.
If I want to know if a system that I have can map onto TOEFL or map onto what you map TOEFL onto to show that it can make AND gates and OR gates, what's the first step to know whether it can compute?
That's a good question. So I have another project that a colleague and I just submitted before we moved on to this TOEFL project. And we took a different game. We wanted to show that that game was hard by reducing it from another one. So that reduction that's tough. I'm finding that that's really, really hard. Choosing which game or which problem to translate from, that's the first step. And then just knowing the problems really well, knowing the games and knowing the problems. This project, what we did was we turned a logic game, like that uses propositional logic, ands and ors, and it's not super fun as a game. And we reduced that game to another game we made up where you're coloring in 2D pictures and stuff like that, which is really fun. So in order to do that, we had to know both of those games really well in order to be able to connect them, to find a way that you can connect them. And I definitely went down the wrong rabbit hole a bunch of times. Working on that one, I spent literally all summer. I have hundreds of pages of notes of incorrect constructions. And then you finally get to the one that's right, and you're like, oh my gosh, that's really good. Yeah. So, sweat. Yeah. And a mathematician, so call me. Thanks.
We're using a microphone? Okay. I don't know if this is in your wheelhouse or not, but the recent discovery, as I understand it, of AlphaGo, the fact that, which was, I think has been thought to be relatively, I think it's AlphaGo, that's been relatively unbeatable, and then they discovered that despite, the latest state of the art, that there's a vulnerability if you surround the thing just so, and it's actually caused a stir within game theory and amongst computer scientists because the vulnerability is generalizable, and you can, if you know what it is, you can actually beat the system pretty quickly, pretty easily. And so it's created all kinds of interesting discussions within the artificial intelligence community. Just wondered if you're following that.
No, I'm really
And so-
familiar with AlphaGo and how
Okay.
it works. Really, really cool stuff. AlphaGo itself was trained on itself.
Exactly, yeah.
So yeah, it's played itself many, many times. It's not like it learned from human players, which if you watch it play, it makes really weird decisions in order to win a game by like half a point that a human player wouldn't do. So because it's been trained on itself and it learns, I wouldn't be surprised if it will improve before long. But no, I'm not familiar with that happening. AlphaGo definitely. So it's an interesting problem because just like chess and Deep Blue and those things, the game is combinatorial. Go is combinatorial, but the system that analyzes it is not. It's statistical. So no, I'm not familiar with that. Now I'm going to go home and read about it.
So if I can just piggyback on that,
Oh, yeah.
another quick question. So there's, and again, I'm speaking way out of school here. I don't know these details, but as I understand it, there's a sort of a big emerging controversy within the artificial intelligence community between the sort of black box folks, which is the most of the community, which just says, let the machine crank away and just feed it more and more and more data, and then it gets better and better in terms of making predictions and solving problems, versus the more engineering approach, which says we need to understand actually what's happening within the black box for various reasons. I'm guessing as a mathematician, you would ascribe more to the latter approach, the idea of that it's important to understand what's actually happening.
Absolutely. I think, and just as an ethical human being, I want to know, I want to bring the philosophers into the conversation too, but if I can go back to war games and just quote it, I mean, I would rather just play a nice game of chess. Right, it's a little scary, but thankfully AlphaGo isn't there yet. But yeah, a lot of the way the AI works, I mean, the way these trained machine learning systems work is black boxed. We don't really know we know how it works, but we don't know what the weights are. We don't know what those values are, and there's some super interesting ethical issues around it. Yeah, I definitely like things as open as I can. Yeah, thanks. All right, you've all been awesome troopers. Thank you for listening to math for an hour. I was told to ask you to stay for food, but you would not have stayed through this just for math. So, thank you. You're all stars.